Test. All right, good morning. Let's get started. Okay, let's finish this variation parameters method today. Okay, but bigger picture, what we have studied in the last few lectures are focusing on this second order non-homogeneous ODE, but with constant coefficients. So this is what I've been focusing on, and we essentially will focus on these two methods. Number one, undetermined coefficient method. So that should jog your mind. You know, the handouts that I give it to you from previous lecture. You have a table, right? And you look up your particular solution based on the form of f of t, and then you start from there. Okay. So maybe I should. Now, variation of parameters is a different approach. It applies when the f of t does not fall onto any one of the type of functions, right, given the table. Okay, so maybe just let me bring up the table here. So this is the table I'm referring to here. So if f of t does not fall into any one of the category over here, so now we should resort to the second approach, variation of parameters. Okay. So note that the following derivation is based on a second order differential equation. Okay, it looks like this. Okay, so now some people have actually probably ask is, so what if your second order differential equation is in the format of this? So they're essentially the same. Now, of course, actually the formula was slightly different, but if you're given a second order differential equation like this, you can always divide A or normalize the first term. So then you basically you get exactly the same format, as this one here. So fundamentally, there's no difference. So what is variation parameter? So we started, okay, so we didn't quite finish, but what we do is, okay, so essentially you cannot take a lucky guess anymore, right? So your particular solution for this second order differential equation, what you do is you let this yp equal to m1 of t times y1 of t and m2 of t times y2 of t. And this y1 of t and y2 of t, they are the so-called basis solution to the homogeneous one. So you always start with the homogeneous solution, right? Yeah. So you have to obtain the y1 of t, y2 of t first, based on the homogeneous second order differential equation. And then you form your y of yp by multiplying y1, y2 with two different coefficients. But this time, the coefficients are a time function, not a constant coefficient. And this is where the name comes from, variation of parameters. So it's like you're varying the coefficients or the parameters, which refer to the m1 of t, m2 of t. Now, of course, the question is, will this type of form for the YP work or not, right? That's what we need to find it out here. So what you do is next you calculate YP prime and YP double prime. Okay. Now, let me see. So let's calculate YP prime first. And when you calculate YP prime, if you recall from the previous lecture, oh, I'll share my screen. Sorry about that. A good thing is I haven't really, just a quick review here for those people online here, okay? This is what we did at the end of the previous lecture for the variation parameters. Okay? So you're letting YP equal to this, and then you calculate YP prime. And after you calculate YP prime, if you recall that, we imposed a condition. And the condition we imposed is M1 prime Y1 of t plus M2 prime Y2 of t equal to 0. So this term is part of the expression for YP prime. So essentially, you forcefully let this term equal to 0. So the YP prime term is less complicated, right? A little simpler. Once you impose this condition, then you calculate YP double prime. Okay? And then we substitute. So if you recall that we substitute YP prime, and YP double prime back into this, the second order differential equation. And after substitution, with some simplification, we end up with, it's particularly, okay, with simplification, okay, because Y1, Y2, they are solution to the homogeneous equation, and the simplification turned out, you will be able to have a term looks like this, which basically 0. So you end up with just simply M1 prime t, Y1 prime t, M2 prime, just a second, yeah, M2 prime t, Y2 prime t equal to 0. So that's the steps that we have gone through. We end up this at this stage at the end of the previous lecture. So I call this equation 1, this is equation 2, f of t. So it started with YP looking like this. and enable a condition, equation 1, and end up with another equation, which is equation 2. Okay. So remember, the purpose is you want to find some sort of a value or solution for M1 of t, M2 of t, so that Yp is actually a particular solution, right? By doing this, you end up with these two conditions here. So let's rewrite the two conditions together. So I have two equations. And what's known here? The known is y1, y2. So if you know y1, y2, you certainly will be able to calculate y1 prime and y2 prime. So this term, the red underlined, they're given conditions or conditions that you could easily obtain by taking a derivative. And what's unknown is m1 prime t, m2 prime of t. And these two showed up in both of the equations at here. So essentially, if you consider you have a set of a linear equation, then you basically have two unknowns and two equations. So I could actually solve like I have a set of a linear equation at here. So now what I'm trying to solve now is to solve for m1 prime t, m2 prime t. So that's the thinking here. The solution for m1 of prime, m2 prime, of course, will be a function of y1, y2, and also f of t. So once you get the m1 prime, m2 prime, and you can integrate to get m1 of t, m2 of t. And that's the ultimate purpose, right? So you can substitute back into this expression for Yp to give you a particular solution. So that's the idea. Okay. So let's take a look at what would the solution look like for m1 prime, m2 prime, and what would the solution look like for m1 of t and m2 of t. And by the way, you don't have to dread too much. Am I required to derive all of these things in final? You actually want. So you will have a formula for m1 of t, m2 of t, right? But I need to show you all of these procedures instead of just show you the final results. Okay. So let's do a little bit linear algebra at here. So I have two equations. Then I'm going to write these two set of equations using matrix format. The unknown here is m1 prime and m2 prime. The matrix here is y1 of t, y2 of t, y1 prime of t, and y2 prime of t. And then here 0 and f of t. So that equation is written in the matrix. And this is basically your matrix A. This is your vector V. This is a vector B. It's like you have A times V equal to B. And you're trying to solve for the V at here. And bearing in mind that this matrix A here is a known matrix. Okay, so you can obtain this matrix A easily. So a linear algebra basically says if you want to get the V, then you need to take the inverse of the matrix of A 2 by 2 times the vector B. Right? Of course, now the question you had to ask is, will I be able to actually take the inverse of this matrix? Okay, that's basically a fundamental question. So now you look at this matrix A here. first row is y1, y2, second row is y1 prime t, y2 prime t. Okay. So this actually circle back to one of our theories when we started learning second order differential equation. One of the theorem that for second order differential equation, if you recall that, right, is, let me show you the lecture notes over there. So this one. So we have a theorem that how to decide on the relationship between two functions or three functions or multiple functions. Is basically look at whether they're linear dependent or linear independent, right? And then we have another theorem basically says if you have two linear independent solution of function which are solution of this function, then you can form the general solution for this homogeneous second order ODE. Okay, so over here the y1, y2, they are basically linear independent of each other. Okay, so then you can form the general solution. So that's how we actually obtain this y1, y2 at here, right? So if you recall the condition that y1, y2, they are the basis solution to this homogeneous second order ODE. So the y1, y2 at here, and they are basically linear independent of each other. Otherwise, then you wouldn't be able to use these two to form a general solution, right? So the matrix you're looking at here is, okay, so y1, y2 are linear independent, then naturally, y prime of t, y2 prime of t, they are also linear independent of each other. So this matrix, basically, whether you look at the row or you look at the column, they're essentially going to be linear independent of each other. And that's the condition that this matrix has a full rank, right? So then you can actually take the inverse of this matrix. So that condition of being able to take the inverse is naturally guaranteed by the condition that y1 and y2 are linear independent of each other. So that's great. So then we don't have to worry about whether we can take the inverse of this matrix or not. So maybe I'll just write on here. Okay. So because y1 and y2 are Li, so A is invertible. That's guaranteed. So now the question is, what is the inverse of this matrix? I'm sure you have, this is 2 by 2. This is a very simple matrix, but I want you to be able to memorize this, okay, 2 by 2. It's not just for this course, I think for any one of the future courses. Okay? When you have a 2 by 2 matrix, its inverse is 1 over AD minus BC, and then multiply by a matrix. What you do is you reverse the order between A and a D. So D here, A here, and then you add a negative sign in front of the B and C. So that's a general format for 2 by 2 matrix inverse. And you can always verify. Okay, remember, if you multiply the inverse with the original matrix, you're supposed to get back with a unit matrix, right? So if you're not too sure, you can always verify. So now I'm going to apply this formula here to calculate the A inverse. Right, here's my A matrix. Okay. I'll calculate the A inverse. First of all, the bottom here, okay, the denominator here, and that's essentially the determinant of this matrix. Okay, whatever this matrix is. So then A inverse, according to the formula, so you first calculate the determinant of the matrix A, then multiply by, okay, using this format. So what I'm going to do, y2 prime showed up in the first element, and y1 goes down here, then you add a negative sign in front of the other two elements. Okay, sorry. So all the primes, the non-prime, right? So just be careful here. This is y1 here, negative y2, negative y1 prime, and y2 prime over there. So that's your A prime. Sorry, that's your A inverse. Okay, so you got your A inverse, and then you can also calculate the determinants of this matrix A. That's determinant matrix A, y1 times y2 prime minus y2 times y1 prime. Okay, so I'm gonna call this determinant. So this term here, I'm gonna call this term, I call it using a symbol, call it W of t. And we also have a name for this. The name for this is called Wronski. It's called the Wronski matrix, W of t. And if you remember, actually, when we learn about linear dependent, linear independent, and I actually have probably quickly mentioned about the Wronski. So the approach that we used to show whether a set of functions are linear dependent or linear independent is that, you know, we form that equation k1 times y1 plus k2 times y2, right? And kn times yn equal to 0. And you look at the coefficients of the constants k's and see if the only solution to make the expression 0 is that all the k is 0. And then you can conclude it's linear independent. So now you actually have a different, basically different approach here is using Wronski. So you could, suppose you have a set of functions, and here there are only two, and you can form a matrix in this format. So if you have two functions, then you form a 2 by 2. You have a 3 functions, you can imagine you form 3 by 3. So the first row is the original function, second row is the first derivative, and the third row will be the second derivative, right? You have 3 functions, okay? And then you can use this so-called Wronski, check the determinant of the matrix. If the Wronski is 0, then you actually have a linear dependent. Otherwise, then you have a linear independent. But of course, in this case, because y1, y2, they are linear independent, so I can certainly say that this W of t is not 0. Right? So the Wronski is not 0 in this case for sure. But you can always use this matrix, Wronski matrix, to verify whether a set of functions are linear dependent or linear independent. So it's a little bit out of the scope of this class, but just a little bit extra additional information, okay? All right, so now you got your A inverse. Seemingly there's a lot of terms involved at here, but just bearing in mind, A inverse is 1 over the Wronski W of t. Now this is something you have to remember, right? So there's no way to simplify it over here. And then multiply by the determinant, by the inverse, by this matrix at here. Basically that's inverse of A matrix A. So what I would suggest is, right, it's very easy to know how to form this matrix A. Okay, so you form the matrix A by using y1, y2, y prime, y2. I want you to spend a little bit of time just to write down a few times of this 2 by 2 matrix inverse formula. Then you will be able to actually write down this equation for the A inverse. So that's what my expectation. And trust me, this 2 by 2 inverse, you will actually use it in many other courses in the future. Nobody will expect you to be able to write down determinant of a 3x3 matrix. But as engineers, on my experience, at least for myself, I always try to remember the determinant of 2x2 matrix. Sorry, the inverse of 2x2 matrix. All right, so now let's carry on. So then I can calculate my solution V using A inverse times B. So bear in mind, V is M1 prime, M2 prime. So that equal to A inverse times B. And A we already calculated. That's 1 over the Wronskian W of T, then multiplied by Y2 of T negative Y2 of T negative Y1 prime, then Y1 of T. So this is your A inverse. And multiplied by B, B is 0 F of T. So now let's calculate this multiplication of the matrix and the vector. So 2 by 2 times 2 by 1 give you back a 2 by 1. So the first row times this column, you get negative Y2 of T F of T. Second row times the column, you get Y1 of T times F of T. There, so that's your solution for M1 prime and M2 prime. Okay. That's not the end of it. Okay, so let's now break it down individually. So first, let's write down the derivative for M1 of T. So this is basically M1 prime. Derivative M1 of T according to the solution here equal to 1 over W of T multiplied by negative Y2 of T and F of T. That's your dm1 over dt equal to this. Separate variable. Remember the purpose to obtain a solution for M1 and M2. So I multiply the dt to the other side. And then we integrate both sides. So separate, that's separating variable here, right? So then you get M1 of T as a solution based on the integration result. Here essentially is a formula which you'll be able to have, okay, for the final. But for now, you know, certainly write a few times, okay, try to memorize it. So you got, this is basically the solution for M1 of T. And as you look at on the left side, on the right side here, right, essentially you ask yourself, am I able to solve this integral or not, right? So first of all, everything on the right side has to be known. So Y2 is known, F of T is known, and Wronskian W of T, which is expression of this. So that certainly can be obtained, and you need to calculate two derivative. So everything on the right side is known, and you put together, you'll be able to calculate the derivative, the integral, right? Okay. And also bear in mind the result of the integral. You don't need a general solution. Okay. The result of the integral, you only need a one, because you only need a one solution for M1 of T. So you're not really looking for thousands of them. You know, technically, whatever results are here should plus a constant, but you don't really need that. Okay, you just need one function for M1 of T. So bear that in mind. So similarly, you can get M2 of T. And that will be integral 1 over this Wronskian and here, and then y1 of T times f of T dt. Okay, so together, these two solutions or results will give you M1, M2, and then you plug it back to the YP function, and that's your particular solution. Once you get the YP and you combine that with your homogeneous solution YH, then you get the general solution for this type of function, equation. Okay, so we got time here. Let's do a few exercise. So the final thing is not that scary. I mean, this is essentially the formula that you're going to apply, okay, to solve that certain particular question using variation of parameter approach. So if you look at this formula, what do you need to know, right? I think really what you need to know is what is this Wronskian W of t? Okay. And other than that, everything else is already there. Okay, so let's look at a couple examples. Let's look at this first one. Y prime, Y double prime plus Y equal to second t. And second t is 1 over cosine t. Okay. Now, of course, we're talking about variation parameters, so we're going to apply that. But if the question didn't really tell you what approach to use, then your initial responsibility to determine, okay, what am I looking at, right? So what you should start with is to look at the terms on the right side, and this is basically your f of t. Examine this f of t. It's not homogeneous, and you only have two different approaches that here learned. One is undetermined coefficient, the other one is this variation parameter. You only use variation parameter if f of t is a type of function that you actually can find the similar form, right, in this table here. So if you look at this table, okay, none of these rows, none of the functions actually give you 1 over cosine t. So then you can carry on and say, okay, undetermined coefficient is not going to work, so we have to use the variation parameters. Right, so that's the logic thinking here. Okay. Yeah. So let's use the variation parameters. Now, when you use the variation parameters, basically means you're going to use these two formulas here. But step 1, you're going to still have to obtain the homogeneous solution first. So basically y1 of t and y2 of t. Step 1, write down the characteristic equation, while lambda squared plus 1 equal to 0. Your solution for lambda has 2 complex conjugate roots. Okay, so positive and negative j. Then you look at your previous lecture notes. When you have a complex conjugate roots, your y1 of t, right, according to this, alpha is 0, beta is 1. So you have basically just the cosine t for y1 and y2 sine t. And this step is critical because if you don't get the right y1, y2, then the rest of the results will definitely inherently be wrong, right? Yeah. Okay, so then your YH is C1Y1 plus C2Y2. So C1 cosine T, C2 sine T. So you're done for the step 1 by obtaining the homogeneous solution. Then step 2, you start to apply the variation parameter approach because you know that this undetermined coefficient is not going to work. So then you look at the formula that you're dealing with at here. You need to calculate this W of t first, right? So W of t, I would recommend that you, instead of just hard memorize W of t, you probably just want to memorize that W of t is actually the determinant of this Wronskian matrix. It's easier to memorize that way. Wronskian matrix is formed by y1, y2 as the first row, y1 prime, y2 prime, second row. the determinant y1, y2 prime plus y2, y1 prime. So, I mean, you can certainly keep the matrix here. So what's y1? It's cosine t. y2 sine t. y1 prime negative sine t. y2 prime cosine t. Okay, so that gives you cosine t times cosine t squared, then minus sine t times negative sine t, which has become positive sine t squared. So it's essentially you end up with a cosine t squared plus sine t squared, which is 1. So that's a very easy Wronskian in this case, W of t. Now you're ready to apply the two formulas for M1 and M2. Okay. So let's calculate M1 first. So y2t f of t over W of t dt. W of t is 1, so that bottom here is 1. y2 of t is sine t, so negative sine t. And f of t is 1 over cosine t dt. So this is your M1 of t. Now you can simplify a little bit. And that give you can take the negative sign out. So sine t over cosine t dt. Okay. So there's no way to avoid integrals. Yeah. But then again, I don't think I'm going to give you very sophisticated integrals, right? The mostly used technique, probably substitution technique, and some other techniques are just simple integrals, right? There's really nothing fancy. So in this case, it is a substitution that you require, right? You can let, say for example, u equal to cosine t, right? But the way I always do is, you have a sine t dt, and that equal to d cosine t, a negative. Okay, so you already have a negative here, so I guess non-negative is gone. Basically, you get a d cosine t and over cosine t. Yes. Did I change the tan t? No, I didn't. Oh, could I change the tan t? You could, but I don't think it's going to help you though. Yeah. So essentially, you're integrating. If you're integrating tan t, I mean, unless you remember the formula for integrals of tan t, right? But I don't require you to remember the formula. As I'm going to show you here, very simple substitution like this. You end up with just what? Ln cosine t. Does that make sense? Right. So essentially, this is like x here. This is like x here, right? If you integral of this, you get what? Ln x, right? Yeah. So I don't think you need to remember formulas for certain tricky integrals. Right? As I have constantly mentioned that the course is not about integrals, but the examination of what you learn in this course. But of course, we cannot avoid integral. So we have to make use sometimes very simple technique like this case to get your result. Okay, so this is your result for M1 of t. Then M2 of t, y1 of t, f of t divided by w of t dt. So this one is easier. y1 is cosine t. F of t is 1 over cosine t. And w of t is 1. Everything canceled out. The end was just a 1. So basically, you end up just a t. Now, if you notice my results written at here, right? I did not add a constant C or B, whatever, right? So typically for a indefinite integral, you need to add a constant. But as I said, I don't need infinite number solution. I only need one solution, right? So if you get a number, let's say if your result is this plus 1, would that be considered as wrong? No. Okay, so it's actually still correct. But you don't need that, right? Yeah. You can just leave it as a ln cosine t. So now your m1 of t, m2 of t are both obtained. Then yp, right, equal to m1 of t times y1, m2 times y2. So that gives us ln absolute sine cosine t times y1, which is cosine t, and then t times sine t. That's your particular solution, yp. So finally, you can see the general solution is with a yh plus yp. So you already have yh, yp, so put them together, now you get the general solution. If the question also gave you some initial conditions, right, then you need to apply the initial condition to solve for the constant C1 and C2. Right, C1, C2 are the constants unknown yet, but if there is an initial condition, for example, y of 0 equal to something, and y prime of 0 equal to something, for example, okay, then you use these two initial conditions to solve for C1 and C2. But otherwise, just leave it as this it is. Any questions on this approach? Right. So I wanted to thinking in, and when you think about these variation parameters, of course, the first step you had to be able to identify them using the variation parameter to do this, right? As a matter of fact, even if your function f is not a 1 over cosine t, if your function f is actually cosine t, you can still actually use variation parameters. So variation parameters is a little more generic. So it can be used to the situation if your function f of t takes a format like this. Okay. But the undetermined coefficient approach, right, is not as generic as this variation of parameters approach. So let me show you one more example. And the examples shown in here is mostly just reiterate or reinforce the idea of the formula for the variation parameter. Step 1. Characteristic equation. Okay. So I just happen to be the same as the previous example. Then y1 of t is cosine t again. y2 of t is sine t. Oh, your yh equal to c1, y1, c2, y2. There you go. That's your yh. The next step, apply the appropriate approach, okay, for the current function. Okay, so this is a function f of t. So now if you look at this f of t at here, according to the logic thinking, now f of t actually in this case, right, is a format of a function in the table, right, for the method of undetermined coefficients. So technically, you can use this method of determined coefficient approach by take a Latin guess for yp, right, with this, and solve for constant n and m. So that works basically. Right? So essentially, in this question, you can use the method of undetermined coefficient to solve that. But I just want to show you why you can also use variation parameters to solve this question here too. Okay. Yeah. I just want to write down. You could use method of undetermined coefficients. But we choose to use variation parameter. That means Wronskian. First, the Wronskian W of t. We need that for the formula. We already done that in the previous example. So W of t equal to 1. That's the same Wronskian matrix, same result. So let's just take a look at the way how M1 of t, M2 of t are calculated. So M1 of t formula, negative y2 f over Wronskian dt, negative sine 2t over 1 dt. All right, so now this is again, there's something that's often in time is a little bit unavoidable. When you have this sine t, sine 2t, there's trig identity, sine 2t is 2 times sine t cosine t. That's sine 2t. And then from here, you get negative sine, there's 2 at here, so sine t squared cosine t dt. Again, you can use a substitution rule to solve this question. So cosine t dt is equal to d sine t. Cosine t dt give you d sine t. So now you get sine t here, sine t squared here. So that's basically the same parameter, right? So then you can solve this as if you're integrating x squared dx. So you get a negative 2, and then times 1 over 3 sine t cubed. Or just a negative 2 over 3 sine cubed t. Here's your M1 of t. So similarly, let's try M2 of t. So let me see, are you comfortable with this sort of substitution rules, right? So just ask yourself, I mean, as complicated as it could go, this is probably what you will see, you could see in the final exam type of question. M2 of t, right, is y1 f of t over w dt. Okay. Y1 is cosine t sine 2t 1 dt. Okay. So apply the same formula, 2 sine t cosine t dt. And you get 2 outside, take the 2 outside, you get cosine t squared sine t dt. Okay. Try yourself. How would you do from here? Give it a try, same approach, substitution, just slightly different substitution. So sine t dt. Okay. So for 1 minute. d cosine t give you a negative sine t dt. So that gives you negative 2/3 cosine t cubed. It's pretty symmetric, right? Yeah. Okay, so this is basically another demonstration of variation of parameters. But this one is particular to show you that it can be applied to the situation where you can use method of undetermined coefficients. Okay, so I think I'm going to stop here. There's still just a couple minutes left. So if you got any questions, feel free to come over. I believe we have a one quiz this week. It's only one question on first order differential equation. Okay, so yeah. Instead of the that's right. Yeah, well, let's just publish that. Yeah, bye.